Hello, everyone. Thank you for attending. As you can see, the title of mine is Private Liquidity Matching Using MPC. My name is Shahla Atapoor, and this is a joint work with Professor Nigel Smart and the other PhD student, Yunus Talibi. And here you can find the e-print version of our paper. Let's have a short overview on the content of the presentation. I will start talking about some introduction, then we'll move on the problem statement and our motivation behind this work, and then we'll talk about our contributions and the algorithms that we propose, and at the end we'll finish by showing the practical efficiency and result of our paper. Okay, what does RTGS mean? RT stands for real time, which means immediately. Gross stands for individually. G stands for gross, which means individually, and S stands for settlement, which means debiting money from the source account and transfer it to the destination's account. Real-time RTGS systems are widely used in modern banking. And in this kind of systems, the transactions are settled individually and immediately at real time if the source has enough money. This system has upside and downside. Upside is that if some bank fails to do its transaction, and then the system will detect it, and this at real time they detect it, and it mitigates the cause of by this failing on the system, opposed to the other system like netting systems, which they are which in those kind of systems the transactions are settled at the end of the day. This is the upside of these systems, and the downside is the problem that this system may have with some liquidity cases. We have three different types of liquidity cases: no queue, gridlock, and deadlock. Let's see what they mean in detail. In no queue, imagine that we have three parties, party A, B, and C. Party A has 25 euros as a initial liquidity. Party B has 10 euros as a initial liquidity, and for example, and so on. And for example, A wants to send 20 euros to party B, and B wants to send 5 euros to party C. In no queue, you can see that all the parties, all the banks have enough liquidity to do their transactions. And in this case, we say that each individual bank has enough liquidity to complete their transactions. And in this case, all the transactions will be settled immediately. In next case, we have gridlock. What does it mean? You can see that in this case, parties do not have enough liquidity to do their they do not have enough liquidity to do their transactions. But if they receive the money which they are supposed to receive from the other bank, then they will be able to do their transactions. In this case, we say that the system has enough liquidity, and if somehow they start doing transactions simultaneously, then this problem will be solved. We will talk about this case a bit more later. Deadlock is the worst case that we have in the cases. And what is deadlock? Again, parties do not have enough money to do their transaction, but even if they receive, uh, even if they start simultaneously and receive the transactions, the money that they are uh, supposed to receive from the other bank, still bank C will not be able to do his transaction because he is receiving 30 euros and he is supposed to send 35 euros. So in this case, we say in the system, we do not have enough liquidity to complete the transactions. Okay, up to now, we saw that if we have enough liquidity in the system, then the transactions can be instantly. But what is happening to the transactions? What is happening if and to what is happening to the to pending transactions? We have two options to solve this problem. In first option, we can inject liquidity to the system, but it may be a bit costly, especially if they get loan or if they borrow. But the second option is using liquidity saving mechanism, such as multilateral netting. In multilateral netting, uh, multilateral netting kind of consists of simultaneously offsetting multiple transactions, and it allows to unblock some of the transactions that they have positive balances. The sources have positive balances. This is the solution to the gridlock resolution problem. And this process is carried out by a central party. Here, a question prompts to our mind that can we remove this central party, this central party? Let's keep this question in mind and go through next two slides and see what does gridlock resolution problem mean. This is a discrete optimization problem. In this problem, we aim to maximize the number of transactions to be settled subject to all the balances should be positive, and the priority of setting the transactions in the queue by banks should be preserved. And the solution given by Betch and Somarki at 2001 is that assuming the transactions are strictly ordered, then they try to maximize the number of payments to be picked from the queue of each bank. Let's see the algorithm in detail. In first step, we include all the transactions to the solution. In second step, we calculate balances for all the banks. And here we face with a condition. If all the balances are positive, then the algorithm will stop and return the solution, which means we already found the solution. But in the case that we have negative balances, even at least one with one negative balance, we will jump to the third step. And in third step, kind of, we are removing the last transaction from the queue of each bank with negative balances. And then this process will continue uh, till either we find the solution or all the transactions are removed from the queue, and then algorithm will return deadlock. Okay, we talked about our introductions, and now let's see what is our motivation behind this work. If you remember, we had a question in mind. Can we remove the central party and do this role with some distributed ledger technologies? This would cause a problem to solve GRP because then in that case, banks need to send all their information to each other to disclose their information. For example, bank A and B, they are going do do some transactions between each other, then they need to disclose their information to bank C, and this is not the case that they want to. What is the solution to solve this problem is decentralizing the RTGS system, which means kind of with a secure distributed algorithm, we can solve GRP in distributed manner. What are the requirements of this distributed RTGS? Are uh, we have three requirements. First one is correctness, second one is fairness, and security. In correctness means that the money which we are debiting from the source account and we want to transfer it to the destination account should be the same. The second one, fairness, means none of the parties, none of the banks should be a favor over the others. And security means that transaction information between two parties should not leak to the to another parties, to the third party. And here it's worth to mention that our work is looking to this third requirements of security with three different definitions of information. Okay, let's move to our contribution. Okay, we propose an MPC-based solution which performs to optimize the liquidity problem in decentralizing RTGS system. Basically, what we are doing is that instead of having a central party, we have a set of parties that they are using an MPC protocol, they are running GRP and they try to solve GRP. In this case, the payments informations will remain hidden as long as these parties do not collude. And these parties are able to run a multilateral netting process in oblivious manner. Let's have a short overview to multi-party computation. In multi-party computation, we have several parties that they have their own inputs and they are going to run a function on their inputs and get Y, the output. This protocol has two requirements. First one is security and integrity of computation, and the second one is that parties should learn just their own inputs and the correct output, and they shouldn't learn anything about the other party's inputs. Okay, in our paper, in our protocol, our setting is in our setting we are using linear secret sharing, which means that a secret is shared linearly, like this example. But this is additive secret sharing. And we write X in bracket, which means X is secret shared. We have linear operations which can be done locally, like additions, and they are free. And we have nonlinear operations which require communication and a bit costly, like multiplication, and they cannot be done locally. In our linear secret sharing is Shamir secret sharing with abort, which means we have a secret which is linearly shared using an entity threshold. N is the number of party, T is the number of malicious party. And in Shamir secret sharing, we have T less than N half, which means the number of malicious parties should be less than half of the all parties. We take a secret as a constant term of a polynomial f, and we give a different shares of this evaluation of this f, this polynomial, to each party. What does abort mean? It means that if a party cheats, the other party will detect and they will abort. And since we have majority honest, so this works. Okay, for our linear secret sharing, for our Shamir secret sharing, we have, in this protocol, we have two phases, offline phase and online phase. In offline phase, we are basically generating the stuff which will be used later in online phase. For example, we in offline phase, we are generating beaver triples. Imagine that we have A, B, C, which are secret, with this equation, with this condition, which is C equal to A multiply B. Beaver triples are generated before protocol starts, and our offline phase is a function independent, which means it can be done independent to any function. In our online phase, we are going to evaluate a circuit with some inputs, and in our circuit we have multiplications and additions. Additions are free because they can be done locally. For example, if a party wants to have a share of x plus y, she can take her share from X and her share from Y and add them together. So we do not need any computation, and with this technique we can compute any linear function. But for multiplication, we need communication, and we are using these beaver triples that we were generated in offline phase. If we want to multiply x to y, first we need to max x with a, and then max y with b, and then using this equation here, linear, using the technique that I explained in previous slide, we can compute this equation here, and we can easily get x multiplied to y. Okay, that was our main idea, and we talked about our setting. Let's move on to next slide. And here I want to show three settings that we have for our algorithms. In all three algorithms that we have, the amount of transactions are secret. But in the case of SODO, we have sources and destinations are open. In SODS, we have sources open, but destinations are secret. In SS, we have all the informations are secret, which means sources secret, sources, destinations, and the amount of transactions are secret. During our implementation, we had different challenges with doing this role with MPC. This is an algorithm given by Somarki, Bechan Somarki, but in addition, we had problems to calculate balances of banks. In the case of SODO algorithm, imagine that we want to calculate the balance of the new balance of bank I, given the initial balance of this bank. Let's denote xzt as a variable, which indicates that if transaction is in the queue or not. First, we set all xt to 1, which means we first put all the transactions in the queue. Then We using these equations here, we can calculate the balance of balance in the new balance of bank I. Here you can see here, this is the A is amount of transactions, and this XT is the things that I mentioned before. This SI is money which bank I sent to the other banks, and RI shows the money, the liquidity, the money that a bank I receives from the other banks. And with this equation, if we subtract the receiving money, the sending money from the initial balance and add the receiving money, then we can achieve the new balance for bank I. In the case of SODSM, as we have destinations are secret, we needed to do something else. We are using a naive implementation, and we demox the index I via a demox array of CTI, kind of, because and here T is the transaction and I is index of the destination. Kind of, we are using this demox array of CTI to we update all the transactions, and in the case that it find the receiver, which is I, the destination, which is I, then it returns 1. So in this case, for SI is the same, but for RI, which shows the money which bank I receives from the other banks, we multiply this with CTI, and the other things are the same. In SSDS, even this is worse because we have sources and destinations are secret. So we need to do the same technique for sources as well. And this is a bit costly. And here you can see that we have changes on SI and R on both of them. And we need to multiply them with the max array that we uh, computed. We had another challenges as well. For example, in MPC, as everything, because everything is secret, it is not possible to say if Z is, for example, equal to 1, do this branch and the other branch. And we kind of needed to do another trick to solve this part, to solve this condition part. First, we defined an array of edge with the size of the number of parties. Then we calculate the balances. If bank I has positive, then we set HI to 0. If the bank has negative balance, then we set HI to 1. And can be done with a special MPC protocol of comparison that we have, like this equation that you can see here. Then we try to detect that if we have negative balance among balances or not, using this equation. We subtract all the terms of h from 1 and then multiply them together and put in a secret value z. Then reveal this z. And here now we have a clear value, we have z. And if z is 1, it means that all the hi were 0, and it means that all the balances were positive, and we already found the solution. But if z is 0, which means that somewhere we had hi 1, and it means that we have one balance among the balances. The other challenge that we had for all the algorithms where in order to remove the last transaction from the queue of the bank with negative balance in a secure manner without leaking any information, we needed to go over all transactions. And here we see that for V, which shows the number of transactions, which is the number of transactions that are included in the queue. With this trick, we try to decrease the comparison that we need to do because comparisons are more costly than multiplication. We are using this multiplication to make the last transaction from the queue of negative bank with negative balance 0. With this one, we first make the last run in the first time that bank has negative balance. With this equation, we make the last transaction 0, and in next times, which bank has negative balance, we are kind of with multiplying an element with previous element. We are making the transactions one by one 0. These are the challenges that we had in our algorithms, and now let's move to our performance and results. Here you can see the result of SODO algorithm, and here is on the right you can see SODS algorithm. This is the time, y-axis shows the time with in seconds, and x-axis shows n, which is the number of parties. And we got our result. We implemented it for 3 different number of transactions: 10, 50, and 100. Here you can see that for the case of SODO, we got better results than SODS. And this is um, because that in SODS we have destinations are secret. And the interesting thing is that when n grows bigger than m, in SODO we have constant because everything is clear, and we get a constant time and constant graph here. But here we can see even after growing the number of parties, when the number of parties grows bigger than the number of transactions, still we do not have a constant time. And this is because that we have destinations secret, and we need to do some equality checks to, or that DMOX techniques that I mentioned to find the destinations. SSDS is even worse, and you can see that for all of them, the other two graphs were better than gave us better result than this one, and this is okay because in this case we have sources and destinations are secret. Okay, up to now we saw the result uh, for one time for one execution. But in practice, we are interested to see the result of our algorithms for clearing the transactions over a day of execution. And the value m, because during a day, the value of m will be changed depending on the transaction size, amounts, and the liquidity of the system. And to do so, we use a simulation methodology given by Somarki and Cook in 2013. What was their methodology? The distribution of transaction graphs are scale free, and we are going to sample S, A, and D, which are source, amount, and destination. And as I mentioned, they are scale free, which means there are some banks that they are doing transactions between each other more than the other banks. So we first set them as N0 and give preferential attachment VB to all the banks. But for these N0 banks that they are doing more transactions, we first set their preferential attachment to be 1, and for the other banks we set 0. Then we define a parameter Q, and we say that whenever Q transactions are generated, then add another banks to the algorithm as well and set their preferential attachment to 1. And whenever banks are doing transactions, I mean they receive and send transactions, their preferential attachment grows. Okay, here is the algorithm that I explained before. Here you can see that in order to sample a source, uh, in this source is selected with the probability of its preferential attachment over the sum of the other parties' preferential attachments. And the same for D is happening here. And um, then we update their preferential attachments using alpha zero point 0.1. And, and here it's worth to mention that we are using, for example, alpha zero point 0.1 because we are kind of following the numbers, the values that the paper that we took our simulator from it. And in order to sample the amount, we take a value x with the normal distribution with mean 1, and we use a standard deviation of 0.2. And using this equation and multiplying degree with x of x, we can get a. What is degree? The degree is the minimum of the in and out degrees of the source and destination nodes. This equation shows that the bigger banks make bigger transaction amounts. And then, as I mentioned before, after that, we make the other banks which are not still in the queue, we set their preferential attachment to 1 and we add them to the algorithm. Okay, to simulate our execution, we need to define another parameter. We need to have liquidity of the system. And to do so, we use a parameter beta to control this liquidity, which is between 0 till 1. And to for initial balance of banks, we need to calculate uh, lower bound Li and upper bound Ui. For what is lower bound? Lower bound is the money that banks need to clear all its transactions at the end of the time window. And the upper bound is the initial money that bank needs to clear all its transaction immediately before before putting its transactions in the queue. And with this equation, we can calculate the initial balance of each bank using beta multiplying beta the to this term of ui minus li. Okay, we first generated the transactions and then we distribute these transactions over 1 hour in uniformly, and then we try to clear these transactions using 2 different versions. In first version, we take transactions one by one, But in second version, we take the transactions are received when we were running the other GRP algorithm and then put them in new GRP algorithm. And at the end, we calculate E and D. And E stands for excess, which means the time that we need to clear all transactions minus one. And if we have E equal to 0, this is perfect, which means our result do not have any delay. And for D stands for delay, which is the average delay that we need for to clear each transaction. And the time, this is a delay, this is the average delay in terms of executed time vs enter time of each transaction. And if D is 0, then which means that executing and clearing the transactions and settling the transactions do not have any delay. Okay, here you can see the table of our results for SODO on the left and SODS on right. Here for E and D, if we have 0, as I mentioned in previous slide, this means that we get better results. And here, if you see that here in the bottom, we have better results than the upper cases, is that we are using beta bigger than the others. And beta is controls the liquidity. Here means that we have more liquidity. So we got better results. N shows the number of parties and M shows the number of transactions. And if you see the results for SODO and SODS, we got very nice results, and kind of we can say that all the transactions can be settled at real time. But for SSDS, as you can see, we have a significant delay. And this delay depends on the number of banks, the number of transactions per hour, and the overall liquidity that we have in the system. To sum up, I would say that we show that we can use MPC to do decentralized RTGS systems, and we can give with MPC protocol, we can give the role of central party to a set of parties to solve GRP in distributed manner. The performance of our RTGS systems are penalized because of nature of MPC protocol. For example, in conditions we need that go through both branches, and for memory access and memory access should not leak any information, and this affects on our performance, and it drops our performance. But still, doing distributed RTGS system with MPC is valuable, as you saw in our SODO and SODS algorithms. We got good results, and we had we could clear transactions at real time. Just in SSDS, we had a significant delay to clearing transactions. Thank you very much.